today we're very fortunate to have Gowthami from University of Maryland, who's going to be telling us about copying and diffusion models.
Okay. Hi everyone. Thank you so much for inviting me for this talk. In today's talk, I'm going to present my work, which I have done over the course of last 1 year. In the process, we submitted 2 papers, and one of them we presented at CVPR recently. And I also want to just give a shout out to my collaborators in this project, Vasu, Jonas, Micah, and my advisor, Professor Goldstein, who helped me out a lot, navigating this whole question we were trying to address. Okay, so I'm pretty sure most of you are pretty familiar with diffusion models. We can just think of them as sequential denoising autoencoders, where we can start from a random noise and we keep denoising until we end up with a realistic looking image. And in most rest of my talk, mostly I will be I'm kind of analyzing stable diffusion, because a latent space diffusion model where the denoising is happening in the latent space instead of image space. And second important aspect is it's actually a conditional diffusion model where all these denoising steps and generations are done based on a condition, which is a textual representation, which is guiding this whole process in the form of a cross attention. Okay. So this slide is sort of old. So 6 months back, when I asked people, okay, do you think diffusion models replicate the training data? I still get a mixed bag of answers, saying some say yes, some say no. But it seems now our paper, and then there is another paper from Google as well, where we found pretty much strong evidence that Stable Diffusion actually memorized a bunch of training examples. So here I show a few images which we found in our analysis. First row has the generation, and in the second row I show the closest match from the anesthetics data set. So as you can see, the first 2 images, mostly the model is remembering the background aspects, the couch here or the Golden Globe Award sign here. And for these 2 images, the model is trying to replicate the content as well. It's just not pixel perfect replication. Okay, so this is primarily the agenda of my talk for today. So first, there is no proper definition for memorization in image domain. I mean, depending the definition can change from person to person. Somebody will say something is copy only if it's exact pixel perfect match, while most of the people believe as long as the most of the content is replicated, it could be considered as a copy. So for our study, we needed to define what are the parameters of replication first. So first I will go through it, and after that we actually don't have any tools of which we can use off the shelf to actually find copies. So we had to search for the tools. And finally, once we found a reasonably good tools, we actually analyzed a couple of diffusion models, and that's where we actually ended our first paper. And we felt that was not the end of the story. We had a couple of hypotheses which we wanted to analyze further to understand why memorization is happening. So in our second paper, we mostly studied what are the I mean based on our hypothesis, we studied a couple of factors and how they are impacting the memorization in these models. And finally, I'll end the talk with a few recipes based on our analysis, which we felt work well in mitigating some of this behavior. So before we move forward, just feel free to interrupt me, if you have any question or if something is unclear. Okay, so let me define what I mean by replication. So for example, we have this query image, and then I ask a person are these 2 images similar? So they might say yeah, they're similar, but they're not copies. But then I kind of show them these 2 images. Now the problem becomes slightly hard. Are they copies? It feels like they are sort of copies because this image came from like part of the query image, and this image seems to be like a collage of the original image and like some other image. Now the definition is not very clear. Is can we count this as a replication or not? And when I show like again these two images, they seem much closer to what someone call it as a copy, like even though like there are some augmentations, some sort of augmentations on these two images. Like for example, we have like a random like a horizontal flip, as well as like some contrast and brightening aspects to it. So on high level, like we can just say, like as we go from right to left, like on the right end of the spectrum, we have sort of semantically similar images to the with respect to the query image, and as we keep moving to the left, like they're becoming more and more perceptually similar as well. Okay, so okay, it's like in our paper, essentially, like we call like all these four types of matches as potential replications. Okay, so this is what the definition which we have given in our paper. We say like a generated image has replicated content if it contains an object that appears identically in a similar image, neglecting minor variations in appearance that could result from data augmentation. Okay, so now that we have defined what we mean by replication, like now we started exploring like are there any existing feature extractors which we can use, like off-the-shelf extractors, like to detect this sort of replication. So the problem with like most of the current data sets to evaluate these feature extractors, or even the feature extractors, is they're mostly like they mostly focus on this sort of matches. Like for example, Oxford Paris, or in some of these retrieval benchmark data sets, like mostly like the query image looks like this and the matches somewhat come from this style. They actually don't account for this type of collage type of images as like potential matches, or they just don't exist in the data set. And similarly, if we look at like a bunch of feature extractors like self-supervised methods, or instance retrieval or copy detection methods, they also mostly focus on these three cases. So first, like what we did is we wanted to find create a data set which can emulate this kind of collage kind of a behavior, and then evaluate like these off-shelf feature extractors on those data sets, on those synthetic data sets as well. So towards that end, we created like a few synthetic data sets. For example, like this is the ground truth image and say query image, and we create like a synthetic image where we took the object and then pasted it on like some random background. So most of these images come from like Pascal VOC and MS Coco, and similarly, like we added like a couple of in painting and out painting kind of create synthetic data sets as well. Like for example, here we took like one diagonal of the image, and we kind of in painted like this diagonal and this half of the image, while we retain like the top part like same as the original image. And similarly here, like we took like a patch out of the original image and outpainted the rest of the pixels. So like we after create these data sets sort of replicate this additional collage type of matches we are trying to find. So after that, like we kind of evaluated 10 different feature extractors, all pre-trained feature extractors. So some of these methods are trained explicitly for like copy detection or image retrieval. And we also evaluated a few like pre-trained models, like which are trained like with classification in mind. And we also evaluated a bunch of self-supervised methods. And we evaluated all these methods across like 10 data sets, five retrieval benchmark data sets, and 5 synthetic data sets. And as you can see, like we computed like the best performing ranks across all these data sets, and we found like 3 feature extractors which did relatively well across all 10 data sets. One is SSCD, which is trained with like a copy detection objective in mind. And we also found like swing transformer and Dino doing like pretty well. Okay, any questions so far? Okay, cool. All right. So now that we have shortlisted like a few feature extractors, so we have like two objectives in mind. Like first one is like we have to test out like if this using these feature extractors, if we can actually find like the replication in diffusion models, and also we also wanted to test like are diffusion models even capable of copying. Like so this was like back in last year September, like so there was no pre-existing literature saying like whether diffusion models copy or not. So that's why we started off with this small um, test scenario where we started off with like a Celibae HQ dataset, which has like 30,000 images. And we trained like 3 models in a DDPM fashion. So each of these models are trained on like 300 images, 3,000 images, and 30,000 images. And once all these models are trained to a certain extent, like where the FID and the FID scores are reasonable and also the generations look reasonable, like then we kind of created a bunch of inferences and compared them against the training data. So here I present some qualitative results. Here there in this case, like these are 3 generations from a model trained on 300 images, and these are the closest top 2 matches based on each of these feature extractors. So as you can see, like for the model trained on 300 images, like the model is able to replicate it like very well. Like I don't know if you can see, like so this lady is like wearing a tiara sort of thingy. The model kind of like copied even those minor details for when we trained on like a really small data set. And it seems like the feature extractors are also doing well, as they were able to like retrieve the exact matches from the training data. And then when we go to like move on to the model, which was trained on like 3,000 images, the model like is not copying the details as much anymore. For example, the background has changed here, and similarly, like this lady, like her lipstick has changed a little bit, and so on. And once we moved on to the image trained on 30,000 images, we did not see any sort of blatant copying in the generations. But I mean, like for example, if you look at this generation, this looks like these two could be related, or perhaps like a same person on a different day. But I mean, I wouldn't call it like a copy. And other than this qualitative results, we wanted to see like if this behavior is like large scale behavior or not. So what we did is for all these models,
Gowthami, is it okay to ask a question, or would you prefer to have them push to the end?
No, sure, go ahead.
So maybe you said this and I missed it, but like those images that you showed us on the previous slide that were generated, like how many kind of were you prompting the model with anything specific, or you were just sort of like there wasn't a particular prompt you were giving the model to get
it was not a particular prompt. Like, so basically these models are trained like unconditionally. We are just randomly sampling.
Okay, and then how many samples did you have to take? Did you run the model just 3 times for each size, or are these kind of the most striking examples out of many runs?
Yeah, so we actually did like around 10,000 generations for each model. And these are actually the images with like top highest similarity scores, like in all these 3 cases.
I see. So these are 3 out of 10,000. That's the right way to kind of think of these images. Yeah. Okay. Thank you.
Yeah, no worries. Yeah, just extending on that thought. Like we also wanted to see like what the similarity score distributions are for all these 10,000 generations in these 3 models. Excuse me. So in this gray curve, like The green curve is sort of like a baseline where we are computing similarity of the training images, each training image with other images in the training set. So that way we'll understand like what is the self similarity within the data set. And then in the gray curve, we are actually showing like what is the top one similarity score of each of these generations with respect to like all the training samples. So as you can see, like there is like a clear distribution concentrated on the right side of this curve where the similarity scores are really high for like 300, the model trained on 300 images, while when we move on to the model with like 30,000 images trained on 30,000 training samples, the baseline like density distribution and the similarity distribution of like the generations more or less seem to overlap. That means like there's more or less no copying happening in this bigger model. Okay, so at this point, like we started to wonder, like maybe diffusion models don't really copy. Like if you train like on larger data sets, and yeah, like maybe the copying doesn't happen. And and then when we moved on to like stable diffusion, we were doing like initial explorations, and then to our surprise, we actually found like a bunch of copies. I mean, like that we are not even optimizing to find these copies. Like we randomly sample a few captions from the training data, and then generate and then find like the closest match, like with in the training distribution. So yeah, like so that was sort of came to us as a little bit of a surprise. And here, like there are different types of copying, as I say. For example, here, like the background is copied, and here, like these two seem like I mean, in the first look, like they seem like exact copies, but if you look carefully, like a bunch of things change. Like for example, the weapon changes in this figure, and so on. So yeah, like after that, like we actually wanted to evaluate like on a larger data set. Um, okay. Right. Okay. We also actually found like a not just the content plus style copying, but we also found instances of style being replicated in the generations. Here, like we kind of tried to like took like some 20 famous paintings and asked the model to recreate these paintings. Like for really famous paintings like Starry Night, the model was able to like content copy content as well as the style. However, like for some of the contemporary artworks, like it's mostly retaining the style but not the content. Okay. And then we actually wanted to evaluate this memorization on a large scale search. Like so this is what we did. At the time, Stable Diffusion v1.4 was the latest model, and this model is actually trained on like 2 billion images from Lion dataset, and it's fine-tuned on like aesthetics v5 plus, which is actually 400 million images. And so we randomly sampled like 10,000 captions from aesthetics 6 plus split, which is actually a much smaller subset. Like it has only 12 million images. And this is the data set like we had on our drive, like at UMD. This is what we did. Like we generated these 10,000 images, and then we compared them against the small subset, which is only 12 million. It's like a fraction of the whole training data. And we wanted to see like, okay, can we somehow quantify the level of memorization even within this limited search? So we found like approximately like 2% of the generations are potential copies. And how we came up with this number is we actually looked through like top 300 or 400 generations. Like so we sorted the images based on the similarity scores with respect to the top one similarity score with respect to the training data, and we looked through them like 300-400 images. We looked through them, and we felt like around 200 image mark, like we found reasonably the models, I mean the images, the generations are not copies anymore. So yeah, that's the number we got. um and then but the thing is like there are so many problems with this number. Like for example, like one question raises like, is this a lower bound? Because like we have searched like the training data which we are searching is just a fraction of the whole training data, right? Like so maybe we did not find like a bunch of maybe we had copies. It's just that we didn't match them to we could not match them to the corresponding training images. Like for example, we have this screen painting. This is one of the caption in this 10,000 captions we sampled, and this is the top match we could find on aesthetics 6+ dataset. However, this image exists in aesthetics 5+ dataset, like which is 400 million images. So that means like we missed out, we did not count this one as a copy in our search. So yeah, because we analyzed like only a few caption, it's not really a lower bound. And again, like is it like an upper bound? Because we kind of actually sample the captions from the training data. And because in reality, like people might or might not use the exact same captions as the training data, right? So however, like we found like a few interesting cases, like where the caption we used for generation and the caption of the matched image are quite different. Like for example, if you see this image, like more or less most of the aspects of the image are copied except for this painting, and we had like 0 word overlap between the caption used for generation and the match. And also similarly, like this is just one more example that falls into the same category. And then we also have like some images with like just one word which matches between like the caption used for generation and the match. For example, in this case, like the bloodborne is the word, like which is common in between. And also like we also found like these interesting cases where a phrase is the one that is like inducing the memorization. So this couch I have shown like already 2 times in this presentation so far. It's like my favorite couch. So this couch appears like whenever you say like canvas wall art print, and you can pair it with like any type of description for the wall art, and it still like brings out this couch like around 20% of the generations, like when we did the study. And similarly, like the great wave is, again, this phrase induces waves in the form of the original painting. Yeah, so there is like you don't exactly have to match the full caption for the copying to happen. You can, even if you match like the parts of the caption, the model seems to be copying. So it's not really an upper bound as well. So yeah, like this number is just an approximation, and we should not take it on the face value. That's the main takeaway here. Okay, so this is like that concluded the first paper which we presented at CUPR, and so basically like we had this mainly from our analysis. What we found is like there seems to be 2 factors which are strongly responsible for like memorization. The first one is the data duplication, and this hypothesis has been around for a while. But the second one, like which we felt like nobody has really explored, is like the effect of text conditioning. As I have shown, like even like certain words or certain phrases can strongly induce like memorization, and so yeah, like that's what we actually wanted to study for our next work. Okay, so any questions so far before we move on to the second one?
I had a question, but you know, maybe this you can tell me to postpone till the end if you like. So it seems like some of the types of copying you're going on, like the caption is referencing something very specific. Like, for example, in the Great Wave example, assuming there's more than a couple of copies of the Great Wave around, even if there's just one, it seems like reasonable behavior for the model to like spit back out something very close to this, like a specific piece of artwork that I'm referring to. Or like in that Golden Globe Awards example, if the caption involved, you know, person on the red carpet at the Golden Globe, then it's like totally reasonable to like replicate that image nearly exactly, because that's essentially what you're asking from the model, right? So is there any like, is this something you guys kind of looked into? Like, what are the different kind of types of replication you might observe? Right? If I ask for an image of like a particular actor, then it's not surprising that I'd get like a near copy of, you know, Nicolas Cage's face or whatever. But if it's coming up on like the couch example is maybe more of a kind of surprising example, or something that seems like more of an undesirable behavior.
Yeah, actually, that's a good question. But so the thing is like, when is replication acceptable? Is not something like we can answer. I completely agree with you. Like, for example, if I'm asked for like, even in the slide I'm showing, for example, like moon landing. Like, for example, moon landing is it's a perfectly reasonable image to generate. But the thing is like, the but this image is copyrighted, and literally like Getty Images is suing Stable Diffusion for generating some of these images, which they hold copyright, right? So I mean, while it is reasonable, while it's true, the model is learning the right things, but I mean, like I cannot really answer like, should the model be like replicating these things?
All right.
Yeah.
It's fine. Maybe we can, if we have time, take the discussion to the end. I don't want to slow you down on that.
Sure. Yeah. Okay. So so in our second work, like okay. In our second work, basically, like we also try to see like so in the first paper we were mostly sampling captions from the training data itself. And in our second work, actually, we wanted to see like, do we actually see this sort of replication in real world prompts, like the prompts which are generated by like human beings when they are using the Stable Diffusion. So there was this data set like called SD prompts or something like that. So we kind of sampled like around 50,000 prompts from there, and then we did we almost replicated the same Stable Diffusion experiment. And these are like the few of the images. Like the first row is the generation, and the second row is the closest match in the training data. As you can see, like some of these images are quite reasonable. The model is actually doing what it is asked, it but the thing is like, technically it should not be like outputting these problematic images, like for example the moon landing here, or the PUBG, which I'm guessing like is the copyright of the game image, and so on. So like, yeah, we initially did a study like so, and we felt like, okay, it's actually problem in on real world prompts as well. Okay. So, I mean, like, so in this second work, like we mainly wanted to test out these two hypotheses, which we have developed like while we were like working on the first paper. So, the first one is the memorization is like high in those images with like really high perplexity captions. For example, like if you take like the word bloodborne or PUBG, these are like extremely specific set of sequence of tokens, which you don't usually see in like English language, right? Compared to like words like a beautiful sunset. And we felt like if you replicate the an image which is like a sunset, and then with a caption a beautiful sunset 100 times, and an image with like PUBG with the caption PUBG, and then replicate it 100 times, we hypothesized that like this image with like highly specific caption, the model is more likely to remember it. So that's the first hypothesis. And the second one was like we also felt like the images which are duplicated along with their captions are more likely to, the model is more likely to remember them than the images which appear multiple times with like a different caption every time this particular image is like found in the data set. So these are the two things we wanted to test out in this paper. So to test this hypothesis, like we actually had to run like a lot of experiments. Literally, like we had to train a bunch of models. So we could not train like a Stable Diffusion level like multiple models of that size. We mainly conducted a study on a smaller data set, where we sampled like 10,000 images randomly from the whole Lion 2 billion images, and also like we also conducted a few experiments on this ImageNet dataset, which is like curated by Fast AI, which has like 10 extremely different classes from like the whole ImageNet. And we kind of like trained all of these. We use like Stable Diffusion architecture for this purpose, and we trained all these models for like 100,000 iterations with like constant LR and other details. Okay, and one important detail I want to mention is like so for all the experiments, like just to maintain the comparability, we've kind of we froze the captions which we are going to use in the inference. I mean, this will make more sense because like this made more sense to us because for some of the for some of the experiments where we were trying to have like more duplication for some images, like we did not want to sample them more during inference as well. So that's why we froze the inference set at the beginning of the like all these experiments. Okay, so okay, now that we have all this set up, now the next problem is like, okay, how do we measure the similarity? In the previous paper, like we use like SSCD for computing the similarity scores and so on, but we don't have like the exact sense of like what should be. I mean, we did not quantitatively measure the memorization in the first paper. Yeah, so for example, like if you remember the histograms I have shown in like Celibate, so the distributions look somewhat like this. Like if you have like 10,000 generations, my similarity score distribution is something like that. So we had to condense this whole histogram into like a single number, just so that like we can compare this number across like different experiments. So for that, like since we observed memorization in mostly in the images with like the really high similarity score, so we kind of like explored like a few metrics, a few percentile cutoffs to kind of define a single number metric to measure the similarity. Okay, so these are like the few plots, a few distributions like of the similarity scores at different percentile cutoffs. On the x-axis, we are kind of varying the amount of training data duplication. I'll like explain this a little bit further. So we kind of like settled on like around 95 percentile, like metric seems to be like a little bit reasonable for us. So we kind of going forward, whenever I say similarity score, it means like what is the value at 95 percentile of similarity score distribution of all the inferences for that given model. Is this clear? Okay, good. Okay, then let's move ahead. Okay. Even though like it was not our primary goal to evaluate how training data duplication impacts the memorization, but for completeness sake, we also conducted a few experiments on how the training data duplication impacts the memorization. Here I show like a plot where on the x-axis where we are kind of increasing, like, so we take like 5% of the data set and then we duplicate it like a number of times, which is kind of controlled by this factor. And while 95% of the images are not like copied, like, but 5% of the images are like heavily duplicated in the training data. And intuitively, as this training data duplication keep increasing, we see like an increase in the similarity score on both like Lion and ImageNet data sets. However, so we also wanted to check like how it's impacting FID scores. It seems like a small amount of training data duplication seems to help with improving the FID scores for like Lion data set. However, the behavior is like very different for like ImageNet. Like we believe like this sort of misalignment of FID score behaviors is because like both of these are quite different data sets. And when I actually looked at like how the generations are like at the high duplications for ImageNet, and it seems like the problem is some of the classes are not like learned really well, and that's the reason why FID was going up in ImageNet. Yeah. Okay. And the next question is like, what about the style impact of the text conditioning? So like I mentioned before, this is one of our the hypothesis which we developed in the first paper, where we felt like the captions with high perplexity, the model is more likely to remember. So to conduct that experiment, so this is what we did. We tried like 4 types of captions. We trained models with like 4 different types of captions on ImageNet. The first style is like fixed caption. So this is essentially sort of similar to unconditional training, where all the images are kind of trained with a caption image that's fixed, and all the images are trained with that one particular caption. And the second style of captions are like class conditional class captions. So the caption will be of the form an image of a dog, something like that. So for since this data set has like 10 different classes, so essentially like this whole training has like 10 unique captions. And the third style is like blip captions, where we took all these 10,000 images and then captioned them using like the blip model. And the fourth style is random caption, uh, like where we just sample random 6 or 8 tokens, and then we assign them to each of the images. So as you go from fixed caption to random caption, the perplexity of the captions keep increasing. And then after we trained the models, we computed the similarity scores. And then as you can see, like when we go from fixed caption to class caption to the blip caption, the similarity scores keep going up. However, the random captions like have like lower similarity score. This sort of misaligns with our hypothesis. But then what we realized is like this could be happening because the clip text encoder do not understand the random captions at all, because because that the text encoder is frozen. Um, so what we did is we actually we have trained the text encoder along with the diffusion model, and that means like during the training the clip is also understanding these random captions. And as you can see, like and here in this case, like there is a sudden shift, like sudden increment in like the similarity scores, because like now the text encoder is also quite aligned with the training data distribution. So this sort of gives like a little bit evidence to our hypothesis that like maybe the model tends to remember those images with like these unique captions. Like for example, Bloodborne is like quite unique. Maybe that's the reason why the models are kind of remembering this particular video game posters, or the movie posters, because these names of these movies or video games are also quite unique, like when it comes to like regular English. Um, any questions so far? Okay, good. All right. So, and then now we kind of move on to the second hypothesis, where we wanted to study like the effect of the style of duplication. Like for example, if you're duplicating both image and caption pairs together versus you're duplicating only images but not the caption. So every time this image appears, like it appears with like a completely different caption. I mean, like at least like not verbatim copy, but a slightly different caption. So we have conducted this study again on Lion dataset. Okay, let me quickly explain. Like these pink curves are where both the image and caption pairs are duplicated together, and the blue curves are where images are duplicated, but we have like every time the image is duplicated, it is mapped with like a new caption. And how we achieve that is like we actually like ran for every given image, we kind of generated like around 20 or 30 blip captions, and every time the image appears, it is paired with like one of these from this pool. As you can see, okay, let's ignore this line for now. And as you can see, like there is a clear difference, like the models which with the full duplication, where image and caption pairs are duplicated together, they seem to have like a higher similarity scores compared to the image models where only the image is replicated. Um, I mean, so like I mentioned before, like we are sort of freezing like the captions which we are using for inference. So because of that, like there is like a slight domain shift. for this particular experiment, because like in the training time, the model is for these particular 5% duplicated images. The model is saying like a different type of captions during the train time, and then during inference, they're coming from like a complete frozen set. So we reconducted the experiment like for this particular partial duplication case with the resampled captions, where we ensure like the test time captions are also coming are kind of similar to the train time captions. So this kind of led us a slight increase in the similarity scores. However, it's still far below like the full duplication. So again, so this kind of gives us like again like some evidence towards our second hypothesis, where it's the model tends to memorize those images with when both the image and the caption pairs are duplicated compared to just the images alone. Okay, so just for the completeness sake, we also conducted a few experiments on like how the length of the training or the amount of training data affects the memorization behaviors. And intuitively, like as you train for longer, the model tends to memorize a little bit more. And also, like if there is more training data, like the model tends to have like slightly lower memorization. Okay, so this is like a one interesting thing we found during our experiments. So this was never on our radar, but what we found is like even those images with so those models with like absolutely zero duplication in the training data, the model still is remembering like few examples, and we just looked through them like and tried to understand like what these images are. And what we observed is like these are extremely simple images. Like for example, the background is like completely white with like one object in the center, like a chair or something like that, or maybe like a simple logo of like some brand and so on. So that kind of gave us an idea like maybe image complexity also plays a little bit of a role in on whether the model will remember it or not. So for that, like we kind of computed two metrics, which sort of resembles the complexity of the images. First one is like the pixel level entropy, and the second one is like the JPEG compression ratio. And when we kind of checked like the distributions of like images with like high similarity score versus the low similarity score, there seems to be like a clear distinction. So perhaps like the complexity of the images also play a little bit of a role here. Okay, so based on this, like mostly in this paper, we were like mostly studying like the impact of the text conditioning on memorization of diffusion models. So we had like a few thoughts like from all these findings. So here I kind of mentioned like a few mitigation strategies. Like for example, in the training time, maybe like instead of training a given image with like a single caption, maybe like have like a pool of captions, and every time this image gets sampled, like maybe like pick randomly one of these captions. So that's one of the interventions we tried. And the second thing is like or maybe like during the training, like randomly replace the caption with like a random sequence of tokens or something like that. And we also tried out like a few inference time mitigation strategies. Like for example, like you can add like a slight bit of noise to the text embedding, or you can just add like a few random tokens or random numbers to the caption, and perhaps like that can alleviate this memorization issue. So I will just show examples like qualitative results from two strategies. Like the first one is this multiple caption strategy. Like I mentioned, for every given image, like instead of like a single caption, like we have like a pool of captions. And in the first row, like we show like the training data, and the second row is like the generation of from a model which is trained without any this mitigation, and the last row is like the generation from the model which is trained with this mitigation. And as you can see, like the results are astounding. And I mean, like I was extremely surprised about like how well this worked. And on the right side, like we present some inference time mitigation strategies. Like for example, like just add like 3 or 4 random numbers to your prompt. Like that doesn't really move the prompt too far away, like in terms of um, yeah, like from the original intent. However, it's enough to break this memorization. So here are a few examples, like some of these examples, in fact, like we picked up from the Google paper, for example, this Anne Graham Smith one. And as you can see, like these sometimes like they change the intent. Like here, it seems like uh, yeah, it kind of changed like the generation by a lot, but however rest of the times like it did not impact the generation too much. And other than the qualitative results, we also have like some quantitative numbers of the models trained with these mitigation strategies. And we found like this multiple caption mitigation strategy works like really well, uh, like when we analyze like this over like 10,000 generations. Okay, so just
Question.
just oh, sure.
So do you think that this like injecting something into the prompt is like reducing the utility of the output? Like if you
Uh,
look at these generations, sort of wondering, is this actually harming utility, or is it like an equally effective answer to the prompt?
so it definitely impacts the utility. As you can, I mean, we actually computed like the clip scores. The clip similarity scores definitely like fell down by a bit. So, but these are all inference time strategies. Like for example, like we tried like Gaussian noise. Like we add like a slight bit of noise to the text embedding, but most of the times it doesn't work really well. However, we found like adding this token or number sort of like broke the memorization patterns most of the time, but however it definitely changes meaning sometimes, like I mentioned here. It looks like the word cricket got embedded, got randomly sampled in this prompt, and then yeah, it changed the meaning fully. uh, I mean, however, like this is like we were doing like in a very like unsophisticated way, because we are randomly sampling the tokens. However, we can actually sample, I mean, if you want to be a little bit smart about it, like you can sample the tokens which are like perhaps slightly closer to the prompt, or just rephrase the prompt. Like that's another way to go about it. So that way, like I mentioned, sometimes the model sort of remembers this continuous sequence of words, like a certain phrases it latches on to. So if you kind of break that phrase itself, like the most of the time memorization goes away. Yeah, David, go ahead. Curtis, David.
Yeah, I have a question. So with this mitigation, right, you like, I guess if you deploy it, it would be for tokens that are copyright, like that have that, like you had a slide, right, with like
Mm-hmm.
PUBG and Mario and stuff.
Mm-hmm.
I was curious, like, did you try it with those and what did it end up looking at? Because I feel like that's when you'd want to do stuff like that, right? For possibly copyrighted like elements that you don't want to replicate.
Yeah, like we didn't test that. That's a good question. We should have tested those. Yeah, but most likely, I mean, not most likely, but I have a feeling it would work. I mean, for example, if you insert like instead of PUBG, maybe you can make it like, I don't know, like add like a number PUB1G or something like that. That immediately breaks like the like that most likely would break the memorization behavior.
I see. I guess the previous question had a really good point where the mitigation will end up like most likely you mentioned that it will reduce the quality of the result, right? With respect
Yeah,
to the
yeah.
prompt, like what is supposed to be a good result if you like provide or if you expect the memorization to return a copyrighted like image, like what should it look like? Should it like not should it generate like nothing or
Um, I I don't know. I don't have the right answer for
yeah.
it. Like I mean, like I don't. For example, like let's say like my prompt is miss like yeah what is it, that Marvel. Uh, like let's say like somebody from Marvel, like maybe
Right,
Iron Man.
right.
Let's take Iron Man. Like it's a very good example. I mean, if you say Iron Man to someone like 20 years back, not from US, like maybe my dad even, he wouldn't know what it means. Like he will probably think like a man made of iron. Okay, maybe that's the right generation. Like this model should be doing, uh, rather than knowing like
Oh, I
Iron Man
see.
is a character.
Mhm. I,
Um,
I see. Okay. That'd be really interesting if that could ever, or you could design a mitigation like that.
yeah. I mean, like, so that style of control can happen only when we are having these mitigation strategies during training. Like I
Right.
mentioned before, like this multiple caption strategy worked really, really well because, I mean, like, for example, some of these cars, like, they have this extremely specific captions, like in the training data. However, when we are like resampling the captions from the blip, like, it kind of removed like some of these specifics, like for example maybe it removed the brand, it kind of just gave generic details like a car or silver car or things like that. So that reduced this specificity of the prompts, and that way like the model remembered them slightly less. However, they're still reasonable generations, like it still learned like to generate good images but not like remember them. Does that make sense?
Yeah, that makes sense. Yeah. Thank you.
And any other questions?
I guess I sort of again, like how were these examples selected? The ones you're showing us?
So the right side examples are actually like these images are actually copied in Stable Diffusion, like 2.1. And that's how we chose them because we wanted to test like inference time uh, mitigation. So that's how these 5 examples are chosen. The left side examples are kind of sort randomly chosen, if I remember correctly. Like I picked from like top 10 or top 20 or something like that. Yeah.
Yeah, I guess I was just curious, like if you look for the, with the mitigation applied, what are the most similar images? Like here you're selecting for images that are most similar with the same caption when you feed the same caption in, right?
Mm-hmm, mm-hmm. Oh, okay. I mean, you're asking like whether I ran like if these images are copies, but just not the original images. Is that what?
Not necessarily. I was just wondering if you run things with the mitigation, like maybe you had this on the next slide and I didn't quite parse it, but like, do you see no, there are no longer any instances of what your similarity metrics deem to be copying? Or
Oh, okay. Yeah. Actually, like I don't have that information on the slides. So even with our best mitigation strategies, we still have some copies, like a very small fraction. Like uh, I okay, these are some numbers I actually computed for something else. So before mitigation, we found around like I don't know, 15% of the images which could be deemed as copies. But after mitigation, around 2% of the images are kind of like seem to be very close matches. Um, s- so 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 even with our best mitigation strategy, we still have like 2% of the images which are copies, potential copies. So and like I said, like these images are very, very simple. For example, Adidas logo, somehow we could not forget it. And yeah, some other examples like that, like some extremely simple e-commerce shirt image. So I think like there are two things which are happening there. First thing is like these images are too simple, and the second thing is like our when we trained this, when generated this like lot of captions for training, uh, I think blip is not is recognizing some of these images, like and it generated like for I looked up only for like Adidas what happened in Blip, so it actually recognized Adidas logo, and out of 20 captions we generated like around 10 of them had like Adidas word in it. So yeah, it's partially because like our captions are not diverse enough, and the second part is like these images are simple too. Like both of these factors are sort of contributing to those, like are responsible for that last 2%, or maybe some other factor which we didn't think of. Yeah.
Thanks.
Yeah. Okay. So for the, I'm almost done. Okay. For my last slide, like if you just want like 2 or 3 takeaways from this whole presentation, I would say like if you do like training data deduplication, that solves like most of the problems, not all of them. And we observed like a SSCD feature extractor is much better than Clip because it was able to capture like partial copies as well. And then another the hypothesis we tested and we found like good evidence is like the models are more likely to remember images with specific captions, or they tend to remember images with these like extremely simple images. And lastly, if you are actually training a diffusion model from scratch, like try to train and if you're doing it like a multiple epoch run, instead of training with like a single caption, like try to train with like a multiple captions. And this seemed to, I mean, this definitely had like really impressive results, like on the small scale experiment. And I'm trying to replicate this. Like we are collaborating with like Stability and kind of like trying to test these methods on like larger models now. And hopefully, like these results will convert there as well. Yeah, that concludes my presentation. And so these are the 2 papers like I presented in this talk. And feel free to like message me or email me, like we can chat more about it if you're interested about this topic.